Assalamu alaikum and welcome to lecture number 26. In this lecture, we're going to further explore the continuous time Fourier transform and we'll be solving some more numericals. Let's consider another example. Here x of t is given by e power minus a absolute of t. So and also it is given that a is greater than 0, so that means this is negative, right? When this is negative, it means it's always exponentially decaying. That means if you move away from the 0, we have expression like, so we have this expression for minus infinity up to 0, and we have this second one expression for 0 up to infinity. So in both cases, if you plot the signal, it is something like this. This is t, and I change the color, so it will be something like this. It will be 0 at infinity, and again it is 0 at positive infinity, right? Negative infinity it is 0, at positive infinity it is 0. So from minus infinity up to 0, we can say this is exponentially growing, whereas from 0 up to infinity it is exponentially decaying. So let's find the Fourier transform for this signal. So it's quite straightforward that we write x of j omega, this is equal to, so from minus infinity up to 0 it is e power at times e power j omega t d of t, plus from 0 up to infinity e power minus at times e power minus j omega t dt. So that means x of j omega can be written as integration minus infinity up to 0. So if I multiply the two, because they are multiplied, bases are same, powers will be added, and it will be at minus j omega t, right? So taking t as common, we get e power, let's take positive t common, so we get a plus a minus in fact j omega dt plus integration 0 to t, again taking minus t common here, so it will be e power minus t, and this will become a plus j omega, a plus j omega and dt. So integration of this will result into, let's write it here, x of j omega, and this is equal to t a minus j omega, a minus j omega, and the limit of integration is minus infinity up to 0, and I forgot to write the scaling here, so it will be a minus j omega plus e power minus t, and we have a plus j omega, and divided by minus a plus j omega, and the limit of integration will be 0 to infinity. So I think that's quite straightforward. You can say that if the upper limit here is 0, so if I put anything 0 here, t0 here, so it will be 0 multiplied by this e power 0 equals to 1 minus the upper limit. So upper limit will be e power minus infinity, and e power minus infinity is basically 0, so I get a minus j omega and plus, again if I put the upper limit here, so it will be e power minus infinity and minus the lower limit, so it will be e power 0 divided by minus a plus j omega. So on simplifying this, I'll get x of j omega, this is equal to, that I get e power minus infinity is basically 0, so I get 1 over a minus j omega, and then e power minus infinity is basically 0 and e power 0 is 1, so 0 minus 1 is minus 1, this minus and this minus becomes plus, so I write plus 1 over a minus j omega, right? So taking the LCM, so LCM will be a minus j omega times this is in fact a plus j omega, right? So like 1 over a minus b plus 1 over a plus b, so the LCM will be a minus right, so it will be a square plus b square, so it will be something like a square plus b is omega square, and on the here we have something like a plus j omega and plus a minus j omega. So you can see these two cancels, right? Minus and this is plus, so I get x of j omega something like 2a over a square plus omega square, right? So that means it doesn't contain any imaginary component, so the phase response, which is equal to right, I just write here this is x of j omega, that is the phase response, so the phase response will be equal to tan inverse, right? So because we don't have any real component here, so 0 minus 0, so that means because in numerator we don't have the real component or let me write the complete, so we have the phase of the numerator, so phase of numerator will be tan inverse, right? You understand, imaginary over real. So if you look at the numerator, we don't have any imaginary part, so that means we have 0, so we can write 0 over real is 2a, and then because it's a denominator, so in case of denominator we put negative sign here, so that is tan inverse. Again imaginary, if you look at this one, is 0, so 0 over what is the real here, so both are real, a square plus omega square, right? So that means this is 0, this is 0, so that means phase response of this signal has 0 value, right? So because you understand that Fourier series or Fourier transform, the coefficients are in general complex. So if something is complex, then we have the phase response and we have the magnitude response. So in case of this particular signal, we have 0 phase response, and for the magnitude response you can put different values of A and you can plot the figure which will be similar to the one plotted here. But I want you to do it by yourself so you get clear understanding. Okay. So let's consider pulse here. So this is a pulse in the time domain that exists from -t1 up to t1, and before t1 minus t1 it is 0, it can be observed easily, and after t1 it is 0, right? So this is just a pulse that exists from -t1 up to t1. Mathematically it is defined as x of t equals to 1 for t absolute is less than t1. So that means this is equal to 1 for t is let me write it in more elaborative form. So we can say that basically this is equal to 1 for t is greater than t1. So we can also write it like this, that x of t equals to 1 from this range of time, right? If t is greater than -t1 up to less than t1, and it is 0 otherwise. Okay, so to solve it, that's quite straightforward. Just put the equation and we know x of j omega equals to integration minus infinity up to infinity minus infinity up to infinity, and we have x of t times the e power minus j omega t dt, right? So based on the given condition, we can say that basically this signal is 1, right? This 1 is for this range. So I can say that minus t1 up to t1, this signal is 1, so I just straight away write 1, right? If I write it, sorry, yes, this is minus j omega d of t. So this is equal to, if you integrate it, you get e power minus j omega t, right? And divided by minus j omega, you understand this is this one, right? So this one will be written here. You understand it involves quite simple integration. So the limits are minus t1 up to t1. So that means x of j omega equals to, so what, by putting the limit, so when I put upper limit, then it will become e power minus j omega t1, right? And minus the lower limit, so lower limit is minus, and this t is also, lower limit is also minus, so minus minus becomes plus, and we get e power j omega t1, right? And the we already have minus j omega here, so if I take minus from this side common, okay, let me take minus common. So if I take minus from here common, so it will become plus, and this will become minus, and I have a minus here. So this minus and this minus, they become plus. So now we have the expression, because it's norm that we write the positive first. So e power j omega t1 minus e power j omega, right, minus t1, and I have j omega here. So if you compare with the sine function, right, if you recall that we can write, okay, right here, sine of theta equals to e power j theta minus e power minus j theta divided by 2j. So it's similar to this expression. So the only difference is if I bring the, let me write it here. So if I bring this is equal to, if I bring omega here and I multiply and divide by 2, right? So I get something like this. Now inside the brackets, this is basically sine. So I can say x of j omega basically equals to, oh, I made a mistake here. This is not omega cannot come here. Omega in fact can come here, right? So omega will be somewhere here, 2 by omega. Okay, so I have 2 over, so I have 2 over omega times the sine of omega t1, right? So if you recall, this is basically a sinc function, right? So the Fourier transform of a pulse in time domain is basically a sinc function, right? So at 0 it will have a maximum value. We have done this one. So if I put omega equals to 0, right, so it will become sine of 0, and sine of 0 is basically 0. Or I can write it in another way. I hope you have noted this. So if I write something like right, so this is sine of omega t1 or omega. So if the x of that means if omega is 0, right, so it will be, so for let me write, if omega equals to 0 by putting, right, because we need to find the spectrum of it, and spectrum is the graph frequency versus the magnitude, right? So that's for phase and for the magnitude spectrum, right? So you either it's a phase spectrum or the magnitude spectrum. On the x-axis we have frequency. Okay, so when we put frequency equals to 0, we have x of j0 equals to 0 over 0. So you understand, for such cases we use the L Hopital rule. And what does it rule say? What does the rule says? It says that you take the derivative of the numerator and denominator. So if you take the derivative of this sine omega t1, and we also take the derivative of this, so in that case it will result into 2, right? So x of j omega will be equal to 2t1 for the when omega is 0. Hope you understand, right? Or if you want, I can write it here on maybe on the next slide. So writing it here, right, so for omega equals to 0, because we get the 0 upon 0 form, so for such forms you understand we use the L Hopital rule. So based on that rule you take derivative of numerator and denominator, right? So if you take derivative of numerator, so it is a sine of omega t1 or d upon dw, right? D upon dw of wr omega. So from numerator you get this is equal to 1, whereas if you differentiate this one, so derivative of sine is basically cos. Okay, you get cos omega t1, and you again take derivative of d upon dw of omega t1, because it's not simply omega, it's omega t1, so you take again derivative, so in that case it will result into t1. So and from here we get 1. So this is something 2 t1, right? So this is the value you get for the omega equals to 0. So when omega equals to 0, if you plot the signal, it will have value of this is right. And you understand for sinc function it is whether it's in time domain or in frequency domain, sinc function has maximum value when its independent variable has a value equal to 0, right? And the first minimum value or the 0 crossing occurs when the value of the omega equals to in this particular case we can write that, right, this we have already done, so let me write it in this color. So we say that 0 crossing for sinc occurs when taking these values omega t1 equals to m into pi, right, where m is an integer. So that means we have omega equals to m over pi t1. So the first 0 crossing will occur when m equals to 1 plus 1. So when m equals to plus 1, that means, right, so m equals to let me write, because it's integer, plus minus 1, so that means we have 0 crossing at omega equals to pi by t1, and we have on the, if we take the negative values, so we have when omega equals to minus pi by t1, right? So at integer multiple of pi by t1, so for example this is pi by t1, this is 2 pi by t1, this is 3 pi by t1, this one is minus 2 pi by t1, minus 3 pi by t1, minus 4 pi by t1, and so on. So on all these values we have the 0 crossing. So for 0 crossing, generalized expression is, because here theta is omega t1, so omega t1 equals to 0, the signal equals to 0 when omega t1 equals to m times the pi. So when m equals to plus minus 1, it has the first 0 crossing on positive and negative side respectively, and so on. So I hope this gives you idea, right? So this is the sinc function. Resulting sinc function is plotted here, you understand, because it's 0, it gives the maximum value, and because when you put the omega equals to 0, we have 0 by 0 form, right? So you understand, for 0 by 0 form we use the L Hopital rule, right? So I think that's all for this example. So the next example we consider is on the inverse problem, that is we are given a pulse and frequency domain and we have to find the its time domain signal, right? So let's do it. So you understand the equation for finding the inverse is x of t equals to integration. You understand, in case of Fourier transform, we scale the inverse Fourier transform, right? If you recall, in case of the Fourier series, the scaling was 1 by t, or maybe I write it here. So in case of Fourier series, we had equation 1 over, right? This is the analysis equation, right? So integration over t and x of t times the e power minus j k omega naught t, right? And dt. So in case of Fourier series, finding the Fourier series coefficients, which is used for the periodic signal, we scale the analysis equation by a factor of 1 by t, or for the case of discrete time, we scale it by a factor of 1 by n. But in case of Fourier transform, the inverse Fourier transform is basically scaled by a factor of 1 by 2 pi, right? So we have the expression for finding the time domain signal, which is equal to 1 by 2 pi integration minus infinity to infinity x of j omega and e power j omega t and dt or dw. Why? Because the signal is in frequency domain, that is, the independent variable is omega, so we will integrate it with respect to independent variable, right? In this case, if you look at this one here, x of t is, in case of x of t, the independent variable is t, so we integrate it with respect to t. But in this case, the independent variable is basically omega, so we will integrate it with respect to omega. So again, if we look at this one, this pulse exists in the frequency domain from minus omega, minus capital omega up to the capital omega. This is the particular value of the omega. This is your omega. So this is particular value of omega, right? This is capital W. So this signal is non-zero, right? And you understand, on this is a frequency domain signal, right? So to get the or to find the time domain signal, we have x of t, and this is equal to, that's quite straightforward, right? You understand, although we integrated from minus infinity up to plus infinity, but this signal is zero from minus omega towards the minus infinity and plus omega up to the plus infinity. So no need for finding that, because it will be zero. So we just take the limit of integration as this. So this is your this one, and again this is this one, and x of j omega is basically 1. It is mentioned here, right? So that's 1. So 1 multiplied by anything will result into 1, because it's the multiplicative identity. And I hope you don't forget the convolution identity. The identity of convolution is impulse, right? So if you convolve anything with the impulse, you get the same thing. If the impulse is scaled, the resulting signal will be scaled by the same factor. If impulse is shifted, so the resulting signal will be shifted. Okay, so we have and e power j omega t d of omega, right? So if I integrate it with respect to omega, you understand, it doesn't matter the exponential signal is getting integrated with respect to time, or with respect to frequency, or with respect to any variable, right? So you get the same. So that means if I integrate it, so this is the scaling factor of 1 by 2 pi, and if I write in the square bracket, it is something like integration of this will be again will result into the same signal, same exponential signal. And here we scale it how much, j by j omega or by j_t. So by j_t. And why by j_t? Because the independent variable is omega. And what are the values of omega? They are yes, minus capital omega, this one, right, up to this. So these are the limits of integration. So what I get is 2 by pi, 1 by 2 pi, and again this is your upper limit, so it will be e power j, right, minus the lower limit, so e power minus, you understand, right? And this has become it's going towards the sinusoidal signal, right, or sine, but 1 over t. And so again we can write it in terms of sine. So if I remove the t from here and bring it here, right, so it will be t, right, t here. And if I scale it by a factor of 2, multiply and divide by a factor of 2, so I get something this, and you understand this is basically a sine theta, right? So I can write it 2 by pi, right, and this will become sine, so it is sine of omega t, right, and divided by t. So again, you can, by looking at this, you can tell that basically this is a sinc function, right? So again, if you say what will be its value at t equals to 0, so when I put 0 here, it will be omega times 0, 0, sine of 0 is 0, and this is also 0, so I get 0 by 0, right, for t equals to for t equals to 0. So that means we can take again the L Hopital rule, right? So by using L Hopital rule, you understand it will be something like using L Hopital rule. So I straight away write, okay, so I just write it will be something like 2 pi, and this will result into derivative of this will be cos, and again derivative of this will be omega, right? And when I put 0, then cos of 0 equals to 1, and derivative of this will result into 1, so we get 2 omega by pi. Right? Oh, I made a mistake, because this 2 will cancel with this one, right? So I will not get 2 pi, in fact I will get 1 by pi. Okay, so that's 1 by pi. So again this will not be 2 by pi, in fact it will be 1 by pi times c, right? So this is the value for t equals to 0, and I hope you can easily tell where will be the 0 crossings. So 0 crossing will be all the points where right, I write here 0 crossing. So 0 crossings will be all of the points where we have what is the yes, so we have t, okay, I write omega times t equals to m into pi, right? So that means for all values of the t where we have m times pi by this capital omega, right? So when m equals to plus minus 1, we have 0 crossing here, right? So we have pi by omega, m equals to 2, m equals to plus minus 2, right? And so on. So I hope you understand this graph, and that's quite straightforward. Okay, right. So if you have any question or any confusion, you can discuss in the live session. Okay, let's consider one more example where we are given the magnitude and phase, and we have to find the time domain signal. Specifically, we are given that x of j omega magnitude equals to 1 from minus 2 up to 2. This is omega, and this is absolute value of x of j omega. And we are also given the phase response, and the phase response is let's from minus 2 up to, let me change the color, so let's do it like this, that we have from minus 2 up to 0 we have value of pi, and this is equal to, right? So this is minus 2 and this is 2, and the value here is minus pi by 2, and here it is pi by 2, right? To find the time domain signal x of t, so using the inverse Fourier transform formula, x of t equals to 1 by 2 pi integration minus infinity up to infinity, and this is x of t, x of omega, x of j omega times c e power minus plus j omega t, and the variable of integration is omega because we are in the frequency domain. So you understand the Fourier transform is generally complex. So if something is complex, it has magnitude response and the phase response, right? So sometimes we are straight away given x of j omega, and sometimes we are given the instead of x of omega, we are given its magnitude and the phase. So that's quite straightforward. To either we are given x of j omega, or we are given magnitude and phase response. So that's quite straightforward, that we can easily find the x of j omega in case we are given the magnitude response, right? Now we have 1 over 2 pi, and the limits of integration are from minus 2 up to 0. We have the magnitude, right, equals to 1, but phase is positive, right? And from 0 up to 2, the magnitude is still 1, but the phase is minus pi by 2. Okay, so from 0 up to this, we have x of j omega equals to 1, and its magnitude is 1, and phase is j pi by 2, right? And we have e power j omega t d of w, and plus we have from 0 up to 2, we have e power, the magnitude is 1, so that's again 1 into, and the phase is, as can be seen here, it's minus pi by 2, so it's j minus pi by 2, and we have the magnitude, this one, and then we have its integration. Okay, so you can easily find that e power j pi by 2 is basically equal to cos of pi by 2, right, plus j sine of pi by 2. Okay, so that means cos of pi by 2 is basically 0, and plus j of sine by sine pi by 2 is basically 1, so from here we get j of 1, right? So that means this whole thing reduces to j, okay, because the scaling factor is multiplied with both the terms. So I just take this 1 by 2 pi common. So now I have j here, right? So it's just 1 by 2 pi times the j here. So I write it here, and I say okay, integration is from -2 up to 0 e power j omega t d of omega, right? And similarly for the second case, if we have minus here, right, so e power j pi by 2, so you understand this is minus pi by 2, and again this is minus pi by 2. So sine of minus pi by 2 basically results into -1. So -1 multiplied by j will result into minus j. So I write here minus j, and then I find the integration, and it's from 0 up to 2, and this whole thing becomes minus j, and we have e power j omega t and d of omega, right? So we can write it like 1 by 2 pi, and integration of this, right? Because j can also be taken as common, so right? So if I take j common, then this is common, and this one is also. So integration of this will result in e power j omega t, and the limits of integration are from -2 up to 0, and minus, again we have the j omega t, and limits of integration are 0 to 2. So this can be written as j over 2 pi, right? And we have, if I put limit here, so upper limit is 0, so e power 0 will result into 1, minus the lower limit is -2, so e power j, and replace omega with -2, so it will be e power minus j 2t, right? And then we have minus, so here the upper limit is 2, so upper limit, you understand that we have a minus here, so it will be something, upper limit is j 2t, and the lower limit is 0, so it will result into 1, right? And you understand this is minus, so if I remove the bracket, so this thing will become minus, and this minus and this minus becomes plus, so I have plus, so 1 plus 1 I get 2, and e power j 2t, and both are minus, so I take the minus sign common, so I get something like j over 2 pi, and I have, okay, let me write it 2, and then if I take common, right, 1 plus 1 is 2, and if I take minus common, then I am left with e power, right? Because normally this is written first because it has positive coefficient. Both of the terms are positive now because I have taken minus common. So this is 2t, and one thing I forgot here is the scaling factor, right? So if I integrate it, so that's j omega t. So j omega t means we have to mention here j and t, right? And again j and t. So we can take j and t common here because it involves both the terms. So I can write here j and t. Okay, so j cancels with j, right? So here I am left with 1 over 2t. Okay, So this one is plus e power minus j 2t, right? Now dividing this and multiplying this by 2 will result into cos. So I can say that this is now basically cos. So I can write it like 1 over 2 pi t, right? And because we have 2 here and we have 2 here, so if I take this 2 common, so I can write 2 by 2, and this is t here also, so 2 cancels with 2 and I get 1 minus, and this is cos of 2t, right? So the final answer is x of t. Should I write here? X of t equals to this 2 to cancel, so we have pi by t, this 1 minus cos of 2t. Right, so it's 1 minus cos of 2t and divided by pi t, right? So this is the final answer. So this is what the time domain signal is. Okay. So let's consider another signal, that is impulse. So we have impulse in time domain. So what will be its Fourier transform, right? So you understand that Fourier transform is basically equal to x of j omega. We denote it by x of j omega, the transform coefficients, and we say the integration from minus infinity up to infinity, and the input signal is impulse of t, so impulse of t, and we have e power minus j omega t, and it's d of t because it's in time domain. So this will be equal to, you understand, from minus infinity up to infinity for all values of the time the impulse is 0. Why it is 0? Because its argument is non-zero. So from minus infinity up to infinity for all values where its argument is not 0, it will be 0. So because it's not shifted, so that means its argument will be 0 when t equals to 0. So when t equals to 0, it has only value. So when t equals to 0, this expression will become, replacing t by 0 will get e power 0, which is equal to 1. So that means we get 1. So that means if I plot the impulse in time domain, it will be something like this, right? This is the impulse in time domain, and then again I plot the impulse in frequency domain. Here the variable is t, and here the variable is omega. So in time domain, if we have something like this is our impulse, right? So it exists at 0, only at one point. So if I try it in frequency domain, that means it exists on all frequencies, right? Similarly, if we have impulse in frequency domain, what will be its value in time domain? For example, we have a signal that is let me a signal x of j omega, right? So, and this is equal to impulse of omega, and we have to find its time domain. That means we have impulse in frequency domain, so what will be its time domain counterpart, not the counterpart, the time domain signal equal to, right? So we can write that x of t equals to summation, right, 1 over 2 1 by 2 pi scaling and integration from minus infinity up to infinity, and we have impulse of omega, right, and we have e power j omega t and d of omega. So using the similar arguments as we had for the while we were doing the transformation from time domain to frequency domain, so using similar arguments we can say that this impulse, even in this impulse will be zero on all frequencies from minus infinity up to infinity, except where its argument is zero. So because it's not shifted, so that means this impulse exists only at zero frequency. So it will have value of 1 only with when omega is 0. So when omega is 0, this expression becomes 1. So this is equal to 1 over 2 pi, right? So impulse in time, exists on all frequencies if we look at in the frequency domain. So similarly, if you have impulse in the frequency domain, right, this is the frequency domain, and if you have, let me select the color, okay, so if it exists only here, right, so this is the impulse of omega, whereas this one was impulse in time. So impulse in time exists on all frequencies. So similarly, impulse in frequency, right, exists on all times and with amplitude of 1 by 2 pi, right? So this is time. So if we have impulse in frequency, it's time domain. So this just basically signifies that time and frequencies, they are the reciprocal of each other, right? So if something exists on for a very, very brief time, so that means it exists in all in all frequencies, and if something exists on some particular frequency, right? So if we talk about the time domain counterpart, so it exists on all times.